Hey guys, welcome to the first lecture for nuclear physics. In this topic, we will deal with nuclear physics and its application to medicine and to energy generation. Let's start. We will start by discussing the nomenclature and some important terminologies of atomic nuclei. Then we will introduce the chart of nuclides and the line of stability at the end of this lecture. For the atomic nature of matter, so we know that atoms are the main building blocks of our matter, as shown in this figure. This is the representation of your atom. It is considered the smallest particle into which an element can be divided without losing its chemical identity. For your atom, the middlemost portion refers to the nucleus, wherein your nucleus can be divided into two, mainly your nucleons. So your nucleons are your neutrons and your protons. Surrounding your nucleus are your electrons or your electron clouds. It cannot be broken up by any chemical means, but they are able to join together to form molecules and other materials. Dalton proposed his model of an atom, and this is often referred to as your Billiard ball model. He defined an atom to be like a ball as shown here, just a plain ball without any electrons or any representation of your nucleus because they were unknown at this time. So this is the model during 1803. In Thomson's model of the atom is mainly composed of electrons, as shown here, this negatively charged electrons, surrounded by a soup of positive charges to balance the electrons' negative charges, like negatively charged plums, surrounded by positively charged pudding. That's why this is also called your plum pudding model. The 1904 Thomson model was disproved later on by Hans Geiger's and Ernest Marsden's gold foil experiment. Rutherford proposed the atomic structure of elements. According to the Rutherford atomic model, the positively charged particles and most of the mass of an atom was concentrated in an extremely small volume somewhere in the center shown here. He called this region of the atom as a nucleus. Rutherford designed an experiment to use a certain alpha particle source of a radioactive element as probes. So your alpha particle source uh, serves as a probe to check the atomic structure of your atom. And this is the Rutherford's scattering experiment. An improved Rutherford model of the atom is made by Niels Bohr, wherein he hypothesized that the electrons orbit the nucleus at certain discrete energy level or energy levels, as shown in the figure. So we have your first energy level here, followed by the second one. So these are your electron orbital. In the Bohr model of the atom, electrons travel in defined circular orbits as shown around the nucleus. The orbits are labeled by an integer called your quantum number. So this is one of your quantum number. So this is your principal quantum number n. Electrons can jump from one orbit to another by emitting or absorbing energy in the form of photons, let's say. So your electrons can jump towards the innermost shell or away from the innermost shell, let's say. Bohr model was a great success in explaining the behavior of the hydrogen atom. Unfortunately, it does not work for helium or other more complex atoms. So the failure of Bohr model led to quantum mechanical model of the atom, which remains our dominant worldview for an atom. This is the electron cloud model, and it differs from the more simplistic Bohr model in which electrons orbit to the nucleus in much the same way as the planets orbit the sun. In the cloud model, as shown in this figure, there are regions where an electron may likely be found. So we have this concept of probability, wherein this clouds represents the probability where an electron can be found. But it's theoretically possible for it to be located anywhere, including inside the nucleus. With the experiment of Rutherford, the positive charge nucleus was discovered, which is said to be 4 orders of magnitude smaller than the size of the atom. So your nucleus is very small. Scattering experiments can give the details about the nuclear properties. In these experiments, we have a certain type of projectile, and in the Rutherford's experiment, so they have used certain alpha emitter as their projectile or as the probe in investigating the structure of your atom. So therefore, it is possible to describe the nuclear interaction between our nucleons, the protons, and the neutrons. Note that this nuclear force is different from the strong force. The strong force binds together quarks, as shown in this figure below, which refers to your up and down quark. Your protons are made up of 2 up quarks and 1 down quark. And your neutrons are made up of 1 up quark and 2 down quark. And we have this gluon exchange between your quarks. Thus, the quarks cannot leave the hadrons, as shown in the figure. These are the things that we should remember about the nucleus. First, about the proton number. Proton number determines the identity of the element, and this is your Z, or your atomic number. Each element has a unique atomic number Z. Proton number never changes for any given element. We have isotopes, which is, I will write here, isotopes. And your isotopes are variants of a particular chemical element which differ in neutron number and consequently in nucleon number. All isotopes of a given element have the same number of protons, of course, because we're talking about the same element, but different number of neutrons. So in this figure, we have the isotopes for your hydrogen. So we have your H1, your H2, and your H3. Atoms of any given element do not always contain the same number of neutrons, as I have stated. And last is nearly all the mass, 99.9% of the atom, is in the nucleus. Now let's check the difference between an atom and the nuclei. The one holding the atoms together is your electromagnetic force. This can be described classically, and it is possible to extrapolate it to the quantum scale. Many phenomena of condensed matter physics is explained by the study of atomic spectra through the rise of quantum mechanics. So this is for your atoms. On the other hand, for nuclei, the nuclear force is much stronger than the electromagnetic force that holds the atoms. Moreover, this is for short range only, your nuclear force, or short range. We cannot describe it classically Thus, we usually do experiments to analyze its properties or through empirical models. The nucleus can be thought of as a bunch of balls that includes your protons and neutrons packed into a sphere, with the radius of the sphere being approximately equal to this. So the radius r is equal to r naught, which is a constant, times a raised to 1/3, wherein your a is your mass number. Nuclei can also be excited to higher states, keeping the number of protons and neutrons constant. These are called resonances or isomers. Nuclei with the same number of nucleons, on the other hand, which refers to the total number of protons and neutrons, are called your isobars. Last is this notation for nuclide. A specific nuclide can be specified using this form, wherein your X refers to your element, your A here refers to your atomic mass number, and your Z here refers to your atomic number, or the number of your protons. A table of nuclides or chart of nuclides is a two-dimensional graph in which one axis represents the number of neutrons. So here we have the number of neutrons at the x-axis, and the other represents the number of protons or the atomic number in Z. So this is your y-axis. Each point plotted on the graph represents a nuclide of a known or hypothetical chemical element. This system of ordering nuclides can offer a greater insight into the characteristic of isotopes than the one we use in your periodic table. The chart of nuclides is also known as your Segre chart, after the Italian physicist Emilio Segre. Your unstable nuclides or radioactive isotopes wants to make themselves more stable. They break down or decay to get rid of some matter and or some form of energy. This chart of nuclides here maps the nuclear or radioactive behavior of nuclides as it distinguishes the isotopes of an element. It contrasts with your periodic table of elements, which only maps their chemical behavior. Hi there! If you have learned something in this video and like my content, please consider subscribing my YouTube channel, JT Academia, and see you in the next video.